Today's assignment will be a distance time graph, and I've not presented this to you guys before, but we're going to look at the basics. You guys have done graphing before, so we're going to look at the basics on what happens when you have distance and time and we want to graph it. So we're basically graphing speed. So we know that describing the motion of an object is occasionally hard to do with words. We came across that in class when I asked you to tell me when is something moving. Sometimes graphs help make motion easier to picture and therefore understand. Plotting distance against time can tell you a lot about motion. So let's first look at the axis. And we've done this before with other things. So here's our distance. Here's our time. Time is always plotted on the x-axis. That's the bottom of the graph. And the further to the right on the axis, the longer the time is. So this is at 0 time here at the corner. And time gets longer, more time goes by as it goes out. Distance is plotted on the y-axis on the side of the graph, and the higher the graph, then the further from the start. So this is at 0 distance in the corner, and we go further away a longer distance as we go up. So we're going to look at 3 graphs here. Number 1, number 2, number 3. Our distance is on the side, time is on the bottom. And they gave us 3 descriptions, and we're going to try to match our description with the 3 charts. So there's one where the car is stopped. There's one that matches the car is traveling at a constant speed. And there's one where the speed of the car is decreasing. Okay, speed of the car is decreasing. Okay, so here we see a car that starts at 0 distance, 0 time. And over a period of time, they didn't give us that period of time, the distance increases. Okay, here we have a period of time that passes that the distance doesn't change. And here we have a period of time where the distance and speed, or time, started at nothing, and then the fairly quickly the distance covered, and then the time that it takes extends, but the distance doesn't get any further. Okay, so think about calculating speed. Speed is distance over time. Okay, distance over time. So here, if we're calculating distance over time in number 2, the time keeps changing, but the distance doesn't. So do we have a car that's stopped? Do we have a car that's traveling at a constant speed? Or do we have the speed of a car that's decreasing? Well, one of the things we want to look at here is that if there's no distance happening, if there's no change in distance, then the car can't be moving. So, because we said that one of the things that has to happen is for us to have a car moving, we must be covering a distance, right? So number 2, graph number 2 matches the description of A. Graph 2 matches description A. And we'll type that in there for you. Because, and this makes it a little bit hard here. And I'll type it down here. Because the car is not covering any distance. It is not moving. And you don't have to type everything in that I have here. I'm going to highlight this for you guys so you can see it. Oh, that didn't help. Hold on a minute. Undo that. I'll get the highlighter out here for you guys. Okay, so we said that it's letter A because the car is not covering any distance, it's not moving. And you don't have to write all of that in. Either one of those descriptions will work. So let's go back to graph number 1. So we already used letter A, so we're between B and C. Is this a car that's traveling a constant speed? So keep thinking. Distance is increasing in a constant way, right? And time is increasing in a constant way. So no matter where we figure out distance and speed on here, they're pretty much going to be the same. Okay, on this one, distance is increasing really shortly, and time fairly shortly, but then look what happens. we kind of get to where we're almost not moving, right? Okay, so we're looking at number one. Is it the car is traveling at a constant speed or the speed of the car is decreasing? So because we see that the distance increases at a steady rate, the time increases at a steady rate, we're going to say that graph number one matches B. And you're going to say, let me get this fixed here. Because distance and time both increase at a steady rate. Oops, I have two becauses in here. We'll take that out. And I'll highlight that for you guys so you can see it. And again, you can use different wording than I do there as far as that, but you want to make sure you're saying something like that. So that leaves graph 3 describing C. And we're going to say that graph B is the speed of a car decreasing because we have an increase in distance, it's fairly slow, and an increase in time that's fairly slow, but then all of a sudden we have hardly any. Look how it hardly goes up there at all. We have hardly any change in distance, but time keeps going on. So this is a car that has its speed decreasing. So we're going to say because time keeps increasing, but distance almost stops. So there's almost no movement. So you can't have speed. You can't have speed if you don't have motion. So we almost have no motion there because remember there's no distance being covered. Okay, I'll give you a few minutes to go ahead and hit pause here and make sure you're all caught up on that part. So go ahead and hit pause and write those in. Okay, you should be back now, and now we're going to match our parts of the graph to the description. So we looked at the things that were happening up here. We're going to try to match these things here. So we've got a line where distance is increasing, time's really short, so we have a decent amount of distance with a really short amount of time. We have starting at 0, we've got time and distance increasing at a nice steady rate. Then what does this normally mean? Straight line across, we've got no change in distance. It would keep going up if there was a change in distance, so just time goes by. So if there's no change in distance, there's no motion there. And then we've got a change in distance. We're moving on again in distance, but it's really, really slow. Our time is next to nothing. Okay, so we're coming back to our original space. So look, if this is our time and this is our distance, look what's happening. We're coming back to our original distance. Okay, this is showing a constant or a speed, and it's a constant speed because it's going up, but look how fast and quick that one went up, and this one's like longer amounts of time. Even though it went to the same distance that went, it took a lot longer time. That went to that distance in that amount of time, very quick. Whatever this amount of time is, it went all that distance. But look at this one. It took this much time for that to curve up there. Okay, so take a few minutes to look at this. Stationary, by the way, means not moving. So stationary means not moving. So you're going to find a place on here, a letter, that shows not moving. Find a place on here that shows increasing speed. Find a place on here that shows slow and constant speed. Find a place on here that shows fast and constant speed. And find a place on here that is showing returning to the start. Okay, go ahead and take a pause and fill that in. Okay, so here's some things you want to remember, and if you want to look at these and go back and check your answers up there if you feel like you're not right, you can do that. So here's your summary. The steeper the graph, the faster the motion. So let's go look at this again. Very steep as opposed to that, so faster motion. A horizontal line means the object is not moving, it is stationary. A curved line means the speed is changing by speeding up or slowing down. Okay, so we've got a curved line going up, so we've got the speed going up. If we had it curving down, then we have it slowing down. Okay, distance times graph. So use the following paragraph and graph to answer the questions 1 through 6. On Saturday, Ashley rode her bicycle to visit Maria. Maria's house is directly east of Ashley's. The graph shows how far Ashley was from her house after each minute of her trip. So before you start answering questions, go see what kind of information they give you. You would expect to see time down here, and they're measuring it in minutes. You expect to see distance over here, and they're measuring it in meters. And so we're doing something in meters per minute. Okay, then we see that these numbers over here go from 0 to 1600 meters. And then we go from time, we see from 0 to 10 minutes. Okay, so let's start looking. You kind of see that Ashley takes off, and in 4 minutes she gets to 800 meters. And then remember what a straight line across means. And then at minute 8, she starts up again, and for the next 2 minutes, from 8 to 10 minutes, she moves up to 1600 meters. That's what you can see right away on there. So let's look at this. We're going to write formulas for this, so just like we did the other day on our things. Everything has a formula. Ashley rode at a constant speed for the first 4 minutes of her trip. What was her constant speed? So you want to write S equals D over T. That's our formula, S equals D over T. And you can see that her time is 4 minutes. They told us that in here. And in 4 minutes, she went 800 meters. So that's our distance. Okay, so 800 meters is our distance, and 4 minutes is our speed. Go ahead and hit pause, set up your S equals D over T, plug in your numbers, and get an answer. Number 2, what was Ashley's average speed for the entire trip? So if you remember from our notes yesterday, or day before yesterday when I was here, and you can go back and refer to them, average speed is the total distance over the total time. So in average speed, you can see she ended up traveling a total distance of 1600 meters in 10 minutes. So your total distance is 1600 meters, your total time is 10 minutes. So set up your S equals D over T, total time over total minutes. Calculate that, go ahead and hit pause. What was her average velocity for the entire trip? That's what number 3 is. So velocity, what's the difference? Ask yourself, what's the difference between velocity and speed? They use the same formula, V equals D over T, but velocity has 2 things where speed just calculates the one. So go back and look in here, and we know that velocity is speed in a definite direction. So you want to go up here and find a direction. So go down here, and you already calculated average speed, so all you need for your difference down here is your direction. So calculate or go ahead and copy your formula from here, your equation, and put it down here with a direction. Go ahead and hit pause. Number 4, Ashley stopped to talk with another friend during her trip. How far was she from her house when she stopped? So what does it show where her stop is on this graph, and then look and see what distance she was from her house when she stopped. Go ahead and hit pause and write that in. We're going to skip numbers 5 and 6, and we'll do those together when I get back, when I show you how to do slope of the line. You can give it a shot if you want to. I have slope of the line at the end of our notes. You can look at it if you want, but if you want to skip that, you can do that for right now. Okay, so vocab practice. You can do this on your own. Get your notes and fill in the vocab that goes here. So go ahead and hit your pause for that and fill that in. And then the last thing you're going to do is you're going to get a half a sheet of graph paper that you can get that from the sub, and you're going to make your own graph that looks very similar to the one up above. And I want you to draw your own graph showing a car going from a stop accelerating quickly for 5 minutes, then not moving for 5 minutes. Show a slow negative acceleration and then a stop. Total time on the graph should be 15 minutes, but you can choose your own distances. So go ahead and get a piece of paper, a piece of graph paper, and go ahead and do your drawing for that. Okay, once you have that done, please turn in your entire worksheet with your graph paper. Make sure you staple it to it and turn that in by the end of the period.